Okay, let's investigate the metric system here. Okay, so before we get into the metric system, let's just look at what system the metric system replaced. All right, so these are the lengths of the English system, and you'll notice some of your familiar ones like the foot and the inch and the yard, and so on. And these values represent the conversion factors. That means there's 12 inches into a foot, 3 into a yard, 1,760 into a mile, and so on. All right, this is sort of the where we would stay normally when we're using the older, this is the imperial system. But it's sort of interesting to realize that this also encompasses a whole bunch of other really weird and interesting measurement values. So if you want to go smaller than an inch, you could realize that there are 3 barley corns in an inch and 4 poppy seeds in a barley corn. And that a poppy seed is equal in size to a line, and that a line is 6 times larger than a point, and a point is 20 times larger than a twip. So it's a crazy system. It came into being over, generations and generations, and it was not really designed from scratch as a measurement system. Okay, it was standardized and formalized way back when in the English Empire, and therefore it spread to North America when the English came here and settled, and to many other places in the world. Okay, the competing system, or the new and improved system of measurement, was designed from scratch to fix some problems that you might notice with this. Okay, so the imperial system works. You can build things with it, you can do trade with it, and so on. But there are some issues that need to be addressed. Okay, so one, the vast number of units. There's too many different units in it. You have to know what they all mean, right? You've got your surveying stuff here. You've got some Roman stuff hanging around in here. I think I saw cubits. You've got cubits. I mean, those come from ancient times, right? You got to know what all of these things mean. They're all cobbled together from sort of different areas of commerce or science even, or architecture or engineering. And each area had its own unit that would be converted back and forth into other units. Okay, so the number of units is an issue. The inconsistent conversion factors. And, when you get away from length and you get into weight or volume, conversion factors become even more crazy. I mean, some real standouts. You've got a 7/8 in there, a 96. Can't forget the 1,760. You've got the 60/80. I mean, trying to kind of keep all of these things straight is probably impossible if you ever had to go back and forth into any of these sort of obscure units. All right. And the third is where these units came from to begin with. So when they were standardized, at some point someone said the base unit in our system is going to be a barley corn, okay, which maybe came back from the foot. I'm not really exactly sure how you build up from there. These were definitely originally based on body parts. I mean, you can see by their names, palms. The inch is about the width of a thumb, foot, finger, and so on. These are from body parts, but they standardized it all back to the size of a barley corn at some point historically. The problem is, are all barley corns going to be equal? Not really, right? So you have to then standardize the size of the barley corn, which may or may not match the actual size of a real life barley corn. To make a long story short, it's not based on consistent or constant, not based on constant physical properties of the universe. All right. So what that means is if every existing ruler disappeared, every you know object that represents the size of any one of these things, if they were to all disappear, if we somehow like lost all examples of these, you'd have really no possible way of recreating this system because you wouldn't know the size of that original barley corn that they looked at, hundreds and hundreds and hundreds of years ago to set up and standardize this system. If you lose the standard that you have, then you lose your entire measurement system. It all disappears. You can't recreate it again exactly as it was. Okay, so the idea that a better system could be devised is quite old, actually. People think the metric system is kind of like a new idea, but during the Enlightenment, many different people proposed that if you designed a measurement system from scratch, you could fix the problems 1, 2, and 3 that you have with the imperial system. So the idea that you could have a decimal-based measuring system goes back to the Enlightenment, so we're talking like the 1670s, 1680s. But the metric system as we know it was officially sort of put into use around sometime in the 1790s. Okay, and this is sort of after the French Revolution. So it's a French invention, sort of. It was first officially put to use anyway in France after the Revolution. Okay, and so what are the features of it? What were the goals of it? Well, one, make it decimal. So what does that mean? Well, it just means that the units grow by 10 or shrink by 10. So that puts it in line with like our normal everyday math system. Okay. What that also means is that orders of magnitude can be used. All right. So what does that mean? Well, it means that instead of having to have a new unit every time you want to get bigger or smaller, you can just use exponential or scientific notation to indicate your sizes, right? So that leads to the second one, 1 unit for length / volume, 1 for mass, 1 for time. Okay, so what were they? Well, that's the meter, square meter, or cubic meter. For mass, it's kilogram. And that's a little bit odd. We'll talk about that later. And 1 for time, and that's the second. Okay, and the third is to base it on unchanging physical attributes of the universe. Okay. So these are the features of the new measuring system, which is also known as System International nowadays, or you often hear it just referred to as SI, the SI measurement unit. Okay, so I mean it means metric, but sort of the agreed upon universal system that pretty much all countries in the world now use, and it is the measurement system used in science, regardless of where you are in the world. SI is used for science. It's just a better system, period. It's too difficult, and the potential to make errors is too large in the imperial system for it to be used in science. Okay, so The main unit of the metric system, as you can probably guess, is the meter. Meter spelled with an R-E, okay? Meter spelled with an ER is like a parking meter. This is the unit in the metric system, okay? It is not this. That is something, but it's not what we're talking about. So the meter. So what is a meter? Well, a meter is the length standard in the SI unit. So where did it come from? Well, it's sort of interesting. They wanted this universal standard. They wanted something that wasn't changing. So what better to use than the Earth itself? All right, so the original meter is based on the size of the Earth. Okay, so we imagine that you've got the equator here. You've got the North Pole here. And you measure how far it is from the equator to the North Pole on a line that runs through Paris. Remember, it was the French that were constructing this. So, you know, how better to make sure that France is always honored forever and ever than base your metric system on a line that runs through the Eiffel Tower, or a line that runs through Paris anyway. And then you take that line, you measure the exact distance of it, you survey it very carefully, and if you take 1/10 millionth of that distance, well, that is defined as being the length of 1 meter. Okay, so the meter, the original meter anyway, is based on the size of the Earth itself. That also then says that the circumference of the Earth would be 4 times that, or 40 million meters, or 40,000 kilometers. So by definition, that is the circumference of the Earth, at least originally. Okay, so why 1/10 millionth? That's got to do with essentially convenience, all right? This measurement system is anthropocentric. In other words, it's based on the human view of the universe, right? We exist at a certain size scale, and our unit of measurement has to sort of line up with that size scale, all right? The universe is obviously much larger than people, and there are things that exist that are much smaller that we have a lot of difficulty detecting, all right? So in terms of the universe altogether, the meter is a fairly meaningless measurement, right? It's sort of a little bit more towards the big scale and so on. But from the human perspective, you know, the meter, which is sort of maybe around like there on a person, it's a nice size. So it's interesting that you go with 1/10 millionth and that's the size that you get, right? This is a nice metric value. If you went with, 1/1 millionth, well, the meter would be 10 times bigger. If you went with 1/100 millionth, it would be 10 times smaller, probably too small to use conveniently. So it's a nice size that fits with sort of the human scale, all right? So convenience is the first one, right? You need a convenient unit that you can relate to, right? No one can relate to like a billion meters, something that big. It's too big, you can't relate to it. No one can relate to like a billionth of a meter, right? It's got to be near a size that we can deal with, all right? It's a good size that we can deal with. And it's a decimal value. It's a decimal slice, if you want, of a distance, of a set distance, a distance that never changes. Okay, so then what happened? Well, this is the official size of the meter as surveyed out off the size of the Earth. And the French made like a master copy of this in an alloy that doesn't rust. So it's like platinum iridium alloy. I don't know if it originally was that because, I mean, we're talking back in the 1790s that this was getting all sorted out. I don't know if they would have had that alloy back then. Maybe they would have. Yeah, probably. But anyway, why platinum iridium? Because it does not corrode with time. All right, so you make a perfect copy. It's like your master meter. It's the master meter. And they actually have like a bureau where they keep this in a vault, or kept this in a vault. All right? Kept in a vault. And it's the standard by which all other meters are measured. Okay, so if this is the official meter, then what you do is you send out copies to all the places around your country and all of your colonies, and they make their own copy of this thing that is exactly the same as your original master meter. And then you build out all of your measuring devices and you measure back against this. And that's really important that you have these like bureaus of weights and measures, which all countries in the world have somewhere, because commerce sort of depends, and building, engineering, everything depends on everybody having the same sized meter wherever they go, right? If if I go to some other place in the world and they're building airplanes there and the blueprints were built in a different country or created in a different country, and we send them there and their meters are different than our meters, we're going to have problems communicating with each other, right? We're going to have problems buying and selling things. If I buy a ton of wheat or something like that, or I mean to send a ton of wheat from Canada to China, say, and they measure there and their ton is different than our ton, and you can see it causing problems, right? So it's important that this international system has good standardization across the board, right? And when you get into science where you're measuring the very, very small or the very, very large, standardization becomes doubly important, okay? So that's why so much effort goes into measurement. Okay, so here's the meter. It's the basis for the metric system, but it really only covers length, right? So you make this master meter, and then you say, all right, this is going to be our only length value. If we want to measure things that are too large to measure with this, we'll use multiples of it, right? So we start with like the 1, right? So we've got 1 meter. And then, if we need some larger measurement, we'll get a unit and it's 10 meters long. And we'll just have a name for that. We'll call it a decameter. Now, deca just refers to anything that's 10 of something, right? Like if I have 10 pens, I could say I have deca pen. If I have $10, I could say I have deca dollar. I don't know if you ever would, but you could, okay? And then if you want to have like something that's even larger, say you want a unit that's 100 meters, right? Notice that it's all meters, right? It's not like this isn't called the meter and then this is called like the twipplecorn or something goofy. It's just 10 meters or a decameter. We just put this unit to modify the same unit, right? So like in imperial, it's like if the inch was your base unit and you wanted a foot, you'd call it like a douza inch, for instance, right? Or if you knew how many were in a mile, which is like, I don't know, somewhere in the 6,000s. Maybe it is 6,000, I'm not sure. But then you'd have to have a word meaning 6,000, right? It's sort of inconvenient, but that's the concept. It's all based back on the meter. So if you want 100 meters, obviously there's not enough room. Well, you call this a hectometer or hectometer. And if you want 1,000, that's where we get into our famous kilometer. All right. And if you want to go smaller, 1/10 of a meter is a decimeter. And 1/100th, well, centimeter. And 1/1000th is the millimeter. All right, so those are all just like little fractions of our original meter. It's breaking it up into smaller and smaller values. You'll notice that this matches up nicely with our orders of magnitude that we did the other day, right? This is at the 0th order of magnitude. It's the origin. This is at the 1st. This is at the 2nd. And this is at the 3rd. This is at the 10th, or -1. This is at the 100th, which is -2. And again, that's because under here you have 2 10s multiplied together, right? And this is at the -3. And this could just really continue till you get values as small as you would ever need, which is, say, the size of, say, the Planck length on the small end. But I mean, realistically, probably the size of protons and neutrons or whatever. Okay, and then you can go to the large size and just continue this on up till you get to the size of the whole universe. And then you've got a measurement system using one single unit that spans the entire size of the whole universe that we live in. So it can measure everything, right? Try doing that with the imperial system, you know? Once you get above miles, there's really not too much bigger. I mean, there's leagues, furlongs. I don't think you're going to measure the distance to the sun in furlongs, right? But you can measure it in, you know, megameters or gigameters or, I mean, light years, but we'll talk about that later. Okay, so we've covered length, which is one attribute that we might want to measure about the universe. Okay, so length is done. That's meters. Okay, length is meters. We can think about volume actually before we move on. Let's think about volume, because we'll often throw around the word liter. All right, and I mean, you can use liters. There's no problem with that. But the question is, where do they come from? Okay, and they actually come from the meter itself, right? It's the cubic meter. So let's draw ourselves a cube here and think that maybe this cube, this, see if I can make it pretty nice. Okay, so imagine we have a hollow cube here, right? So we've made a cube, and we'll say that this cube is 1 meter on each side of it, right? That would then make the volume of the cube 1 cubic meter. So you get a sense, I mean, we could probably just draw, you know, I don't know, a person here. You know, you're probably maybe about that big. I think if this person crouched down, people crouched down, you could probably put about 4 people crouched in sort of a ball inside the cubic meter. That's about how big it is, okay? So before we move on, I just want to make note of a couple of things about this. The first is, if I have 1 meter, okay, we know that in that 1 meter there's, say, 100 centimeters, right? But in a cubic meter, how many cubic centimeters are there? Sometimes people's first instinct is to say, well, there's 100 cubic centimeters in there. That would be incorrect, wouldn't it? Because on each of these sides, you have 100 centimeters, right? These are equivalent. So you've got like 100 times 100, which I think should be 10,000, times another 100, which brings you to 1,000,000, right? So inside a cubic meter, you have 1 times 10 to the 6 cubic centimeters. Okay, so now that you have a measure of volume here, you can actually define some things about this, right? So instead of using cubic meters or cubic centimeters, okay, someone at some point said, if we take 1/1000th of this volume, okay, 1/1000th of this volume, we will define this as being the liter. Okay, we'll define that as being the liter. Okay, what is 1/1000th of 1,000,000 cubic centimeters? It's 1/1000th of 1,000,000. Well, if 1,000,000's 1,000 thousandths, it should be 1,000, right? So 1 liter is also the equivalent of 1,000 cubic centimeters. All right? This is the preferred SI unit. Actually, not really. Should be careful. It's actually this. It's the cubic decimeter, which is always also equal to 1 liter. So how do we get to a cubic decimeter? Well, a decimeter is 1/10 of a meter, right? So there's 10 decimeters on each of these sides. So 10 times 10 times 10 means there's 1,000 cubic decimeters inside of here. And by definition, there's 1,000 liters in here. So 1,000 cubic decimeters equals 1,000 liters. All right? Or 1 cubic decimeter equals 1 liter, which is the same as 1,000 cc's. Okay? So that's how we convert back and forth between these things. And that is actually the convenience of the metric system, right? You can convert between volume units and length units and sort of metric volume units fairly quickly. Now, the liter is not really part of SI because it's unnecessary. You don't really need a specific unit of volume because you already have length units that can just be cubed and work for volume, all right? So now, how do we get to mass? Well, you take your cubic meter and you fill it with the ubiquitous liquid water. Okay, you fill it with water, right? There's water everywhere on Earth. You fill your cubic meter up with water, but not just any water, it's distilled water. And it is at 4 degrees C, all right? Why 4 degrees C? Well, water's weird in that when it freezes, it actually becomes less dense. So it gets more and more dense as you cool it until 4 degrees. When it starts to begin freezing, then it becomes less dense. So this is where water is at its most dense. So it's distilled because having solutions throws off the measurement. I guess basically as soon as you start adding, say, salt water to this, the density of salt water is going to be different. So something you can always get from Earth is distilled water. Water's everywhere. You distill it, you put it at 4 degrees, you fill your cubic meter with it, and then you define a mass unit based on that. You say this will be equal to 1,000 kilograms. You say 1,000 kilograms is the mass of 1 cubic meter of water. All right? So that's where our mass units originally came from. All right? And that has some implications for this. What it then means is if there's 1,000 liters in here, then we would expect that each liter then must weigh 1 kilogram if it's water, which is a very convenient way of working back and forth between mass units and length units, with length units based on the size of the Earth to begin with. Okay, so the mass is defined then, just one more time, as basically 1/1000 of the mass of a cubic meter of pure water at 4 degrees Celsius. Okay, that will give you exactly a kilogram. All right, at least originally. Originally, that was the plan. So now we have another unit taken care of, right? We've got our M, and now we've got our K for kilograms, right? So 1 kilogram of pure water is what is equal to 1 liter. All right, so you can figure out a liter from mass, and you can figure out mass from a liter, or a cubic decimeter as we prefer. So the last thing that we need to cover is time. All right. Oh, and you might wonder, like, why the kilogram? It's a long story, and there's a great video about it, and I'll maybe link to that. It's good. It's Veritasium. I don't know, maybe you've seen it already, but it's awesome. It just talks about the, why it's the kilogram to begin with, and the convoluted history. I mean, this seems simple. This is the original intent of where you get a kilogram from, but it's a lot more complicated than that. And they're trying to actually right now standardize the kilogram in a better way than this, in a more precise way. Okay, so time. Time is the second, and time is the oddball in the SI unit, okay? Because we don't measure time decimally, do we? We measure time circularly. So here's a circle, right? And let's imagine that it's ancient times, and of course, in ancient times, we all know that it is a fact that the sun goes in a big circle around the Earth, right? The Earth is the center of the universe, and the sun rips around it, right? We know this is true in ancient times. Obviously, it's not true now. We have a solar system, and the sun is the center. There's irrefutable proof of that. We're talking ancient times, like 6,000 years ago, okay? And if you are on the Earth 6,000 years ago, you might want to know what season it is because you are a farming civilization, right? So if you're a farming civilization, you might build things that help you keep track of the sun. Like you might say build like an obelisk, like a tall tower, say, right? And you might notice that at noon, each successive day, the shadow that your obelisk casts moves just a little bit, right? The sun's not in the same place at noon every single day. You'll find that like sort of interesting. Oh, okay, so if I measure at the same time every day, I will find that the shadow of my obelisk is a little bit different in the angle that we have for it, right? We know today the reason that is because the Earth has tilt. As the Earth goes around the sun, right, the tilt to the sun changes on a daily basis. All right? So the question is then, well, how far would we expect the sun to move along the ground? Like if we say put this down. Or we could even be more creative. We don't want to build just an obelisk and mark the ground. We could build like a gigantic like ring on like huge stone pillars. We could like use it to like mark as time goes by, right? Make it like so huge that it like won't move for generations. And we'll line it up such that on like important days of the calendar year, the sun is shining through certain different parts. We'll put like little marker stones out here. And we'll notice that, you know, the sun moves the same distance each day as we go by, right? Moves a little bit. Now, how many different points would you expect there to be on here? Let's say the sun does go around in a perfect circle, right? We'll step away from true astronomy a little bit and be a little bit loose with this, but you would think that there are how many days in the year? You'd probably figure out that there's 365, right? But that's like sort of a nasty number, isn't it? But you know what number's pretty close to that? 360 is, right? 360 is pretty close to 365. And this is divisible by like a gigantic amount of different numbers, like 5, like 10. We don't really care about those. But by 12, by 24, and by 60, right? All of those will divide into this evenly, right? And then you start to think, oh, okay, so the sun, now this isn't exactly right? Because what happens is you wax and then you wane, depending on where you are in the year, right? But if you start marking out your circle, all right, and you figure out, okay, this moves so far every day, and you sort of work out, well, it's not 365 isn't convenient, let's standardize it to 360. What you then end up with is the system that we inherit from ancient times, a circle with 360 degrees around it. Okay? And then that is used to delineate out our clocks, right? Our clocks aren't exactly 360 of anything, but there's 3,600 seconds in every hour, right? 60 minutes. Each minute has 60 seconds. So there's 60s in there, and there's 24s, and there's 12s. Okay, so the circle is 360 degrees, and each degree is split up into what? Minutes. And each minute, if you're talking still about a protractor, each minute is divided up into seconds. Okay, and that is a corollary to the clock. So where does that come from? Well, it's astronomical. So our time is based on astronomical observations. If for whatever reason, it took the Earth like 400 days to go around the sun, the unit 360 would not be associated with the circle. There's nothing about a circle that gives you the number 360, besides the fact that the ancient people noticed that when they're keeping time astronomically with obelisks or things like Stonehenge, that you get this rough motion of the sun and the shadows and where they point, and that roughly correlates, not exactly because it's 365, but pretty close to that convenient number of 360. All right. The ancient Babylonians actually had a base 60 number system, as I recall. Okay, a base 60 number system, and then you get other interesting things that come from that. 5 12s is 60, so you can pull a 12 out of that. 12 is a convenient number to use for things, right? Why? Because you can get 1/3 of 12, can't you? What's 1/3 of 12? What's 1/4 of 12? What's half of 12? Okay, can you do that with 10? Well, you can do half. Half of 10 is 5. What's 1/3 of 10? Yeah, it's like a decimal value, right? Can you get 1/6 of 12? It's 2, right? 1/6 is 2. So you get 1/6, 1/3, 1/4, a half. It splits up nicely. 10, not so much, right? So it sort of makes sense. Like, I mean, we tell time, we say it's 1/4 past, right? 1/4 past, that works back to 15 minutes. Half past and so on. It's not as convenient to split up 10. 10's convenient for a lot of other reasons, but 12 is a nicer number. So you can see the attraction that you might have for non-base 10 number systems. They have uses in certain places. The old British money system was based on 12s, the pence and all of that. And then they went decimal. But, you know, and we have a decimal money system in Canada and always have. But there have been times where people have used 12s. Baking, for instance, right? Everyone bakes in dozens because it's easy. I want a half dozen Timbits, please, right? Or whatever. It splits up nicely. Or, you know, 2 3/4. You can get 3/4 out of this as well, and so on and so forth. Nice and evenly, and they make whole numbers. All right. So I could see that that would be the attraction to time, right? Because you might want to say, well, why isn't time just split into tens like everything else? It's historical, and there's a convenience to using 360. It splits up nicely. Like, you know, 1/4 of it is 90, for instance, right? Half of it is 180. You get a lot of whole numbers out of there, okay? So there we go. Now, once you get to the second, though, and you start to get smaller than a second, everything is decimal below that. So technically, things like the minute and the hour and the day and so on that we commonly use are not SI, but the second is SI, all right? And that just goes back to how the Earth moves around the sun. That's where we get the second from originally, all right? It takes 24 hours for the Earth to go once around the sun, or sorry, not go once around the sun, to spin once on its axis. And it does that 365 times as the Earth goes once around the sun, or 360 because it's a nice round number. All right, so this leaves us with the units that we need to explore in the metric system, which are M, K, and S. There are other base metric units, or SI units, but for us right now, this is all we really need. There's ones for temperature, that's the Kelvin. Brightness, that's the candela. Electricity, that's the amp. Number of things, that's the mole. I'm trying to think if there's any other ones. I don't think so. But for us, M, K, and S, and we're good for a little while. All right, this stuff will come later. That's it.